Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, hi everyone. We're going to start with the last session of talks, 3 talks, and I'm sure you still have some mental energy to kind of listen and mainly like asking questions at the end. So the first talk is unsupervised dependency parsing with transferring distribution via parallel guidance and entropy regularization. And the presenter is Max.
Hello everyone, my name is Xuezhe, and I'm from Department of Linguistics, University of Washington. And our work is about dependency parsing for resource-poor languages which have no label training data. And our idea is to use parallel and label data to transfer distributions from the parsing model of a resource-rich language. And this is a joint work with my advisor, Xuezhe. This is the outline. First, I will introduce our task, and then I will describe our approach and show our experiments. And at last, I will get our conclusion and discuss some possible future work. First, let's see what our task is. Here is an example of dependency tree. It is projective, meaning that there are no crossing edges in this tree. Sometimes we can use some labels on the edges to represent the dependency types, but in our work we do not use edge labels. In our scenario, we assume that we have 3 kinds of resources. First, we have a resource-rich language with labeled monolingual tree bank. We denote this language as source language. And second, we have parallel text between resource-rich and resource-poor languages. And third, we have unlabeled text for resource-poor languages. And we expect to develop a monolingual parser. Here, monolingual means that the test data are in only one language, do not have to be bilingual text. And this slide gives some related methods. We have no time to go into the details. We will compare our systems with all these existing systems. In the following, I will describe our approach. Our method can be summarized as estimating the transferring distribution from an English parsing model. Here, the transferring distribution is the distribution projected from an English parsing model. We will describe this in the future. And by using the transferring distribution, we can transfer cross-lingual knowledge between the target and the source languages. The parsing model we use is the edge factored parsing model, which is a kind of log linear model. Here, X is an input sentence, Y is a valid path. Tx is a set of all possible dependency passes for input X. F, J are the fixed functions, and lambda are the parameters of the parsing model that we need to learn. Weight function, for the weight function for edge E, it first sums over all the features belongs to the edge E with the current parameters lambda, and then it takes the exponent function. By using the weight function, the conditional distribution can be written as the multiplication of each edge's width, and here Cx is a normalization factor. In supervised case, a common method for model training is to minimize the negative likelihood function with respect to a set of labeled training data. But in our scenario, we do not have labeled training data. So the way we used to solve this problem is to minimize the expected negative likelihood function, where the tilde p is the transferring distribution that reflects our uncertainty about the true labels. As mentioned above, we assume that we have a set of parallel data P and a set of unlabeled sentence U. So we can divide our objective function into two items, Kp and Ku, where Kp is the contribution of the parallel data and Ku is the contribution of unlabeled data. Here we introduce a parameter gamma as a trade-off between Kp and Ku. The next problem we need to solve is how to define the transferring distribution. For unlabeled data, we take the transferring distribution to be the actual current distribution in our parsing model, which is p lambda. It is reasonable since that we know nothing about the distribution of the unlabeled data. But for parallel data, we define the transferring distribution by defining the transferring weight function. Here, tilde w is the transferring weight function, and we is the weight function of English parsing model p lambda e. And et is an edge in the target parse. So if et is aligned to an edge es in the source set, then its transferring weight is equals to the weight of its corresponding edge es in English parsing model. Otherwise, the transferring weight for et is equals to its delexicalized form. So here is an example to interpret the definition of the transferring distribution. Suppose that we have a pair of sentences, and here German is the target language. And the length between the two sentences denotes the word alignments. Since the word alignments are generated automatically, so they are not perfect. Now suppose that there are two edges in the target parse. According to the word alignments, they are aligned to two corresponding edges in the English sentence. So according to our definition, their transferring weight equals to the weight of their corresponding edges in the English parsing model. So here we use different colors to distinguish the different edges and the different equations. But for the two red edges, they are not aligned to any edges in the English side. So for these two edges, the transferring weight function equals to the weight of their delexicalized form. For example, for this edge, we keep only their part of speech tags and drop all the lexical information. So the optimization algorithms we use to optimize our object function is the limited memory BFGS, and to calculate k prime function and its gradient, we use the inside-outside algorithm. The complexity is O(n)q. In the next section, we will show the result of our experiments. The tree banks used in our experiments are Google Universal Tree Banks, both version 1 and version 2, and the tree banks from Xuezhe tasks. For parallel text, we use Europale corpus version 7 for European languages and use the KIST corpus for Korean. The unlabeled data come from the training portion of each tree bank. For word alignments, we use Giza++, and for part of speech, we use the universal part-of-speech tag set proposed in Petrov 2011, and we use the Stanford part-of-speech tagger. This slide gives the systems we ran in our experiments for comparison. DTP is the direct transfer parser proposed in McDonald 2011. We re-implement this system, and the result of our experimentation are marked as DTP tag. PTP is the projected transfer parser, and we also re-implement this system and denote it as PTP tag. The negative U and positive U are two versions of our approach. For the negative U are our approach training on only parallel data, and the positive U training on both parallel and unlabeled data. OR is the fully supervised parser, which can be regarded as an oracle. Here are the results on Google Universal Tree Bank version 1. The left three columns are the baseline systems. The two columns in the middle are the two versions of our approach, and the OR are oracles. We can see that our approach significantly outperforms all the baseline systems across all the 5 target languages. And here are the results on the Google Universal Tree Banks version 1, and we can get the same thing with the result on version 1. We also ran experiments on different amount of parallel text. This figure is the UAS on German. Here the x-axis is the number of parallel sentences, and the y-axis is UAS. And blue bar are the results of projected transfer parser, and the orange bar and gray bar are the two versions of our approach. For other target languages, we obtain the same observations. We also ran experiments on the tree banks from Kuno shared tasks. Here are the results for 8 target languages. Here DMV is a purely unsupervised dependent parsing model, and the 4 columns in the middle are the baseline systems. Here is our result, and the OR is oracle. We can see that our system achieves the best result across all the 8 target languages. And under experiments for the experiments on Kuno tree banks, we compare our results, compare our systems with more comparison systems. We compare with the weakly supervised systems, the phylogenetic grammar induction model, and the unsupervised parsing model with non-parallel multilingual guidance, and the posterior regularization approach. Table 4 are the UAS on sentence of length 10 or less without punctuations from Kuno shared task tree banks. Here, the 4 columns in the middle are the new comparison systems, and next to you is our approach. We can see that our approach achieves the best result on most target languages. Conclusion and future work. So in our work, we propose approach for the dependency parsing for resource poor languages which do not have labeled training data. And our approach can be used in a completely monolingual setting, and our approach achieves better parsing performance on 3 datasets. For future work, first we can extend our approach to non-projective parsing by replace the Shannon entropy with Rini entropy. And another way is to extend the transferring weight to higher order parts by defining the transferring weight to higher to the parts that involve small edges. And another way is to replace the parallel text with IGT data. So that's it. Thank you.
Is any questions? Okay. Actually, I have one question. You mentioned at the beginning this parameter gamma that is trading off between the two probabilities. So I was wondering how you
how to choose the gamma?
How you train that, or how you set the parameter?
Yes. For the parameter gamma, since that we assume we have no label data, so we do not want to tune the gamma using the development set. So in our work, we choose the gamma according to the ratio between the number of tokens of the parallel data and the unlabeled data. So for example, if the parallel data has 10,000 tokens and the unlabeled data has for example, 10 times of the parallel data, then the gamma, we choose the gamma 0.1.
Very interesting work. I was wondering if you happen to look in the amount of improvement you get as a function of the specific target languages you used in terms of how freer order they are compared to, say, English, which you probably used. Is there any correlation between some characteristics of the target languages, like free order or not free order, or the extent of the freer order they have compared to English?
Sorry, the question is, sorry, I don't understand your meaning of free order.
So, English, for example, it's very, the order of language of the word order is very rigid. This is how you know basically that subject versus object, because subject, say, would come before the verb and object would come after. In other languages, you might have other cues like morphological inflections and so on. Maybe it doesn't matter for your approach. Maybe it does. I was just curious if you looked at that.
I think you know, we have the experiments on Korean. I think Korean and English have different word orders. So, and we can see our results on Korean here. So for Korean, we can see we also we can see that for Korean, if you use the direct transfer parser, then the parsing accuracy is pretty low. But if we use our approach, we got significant improvement. So I think since that the word order may affect the accuracy of the word alignments, so maybe that's one factor that may lower our accuracy. So, but I think for our approach, it not be a big factor.
Super quick one.
So if you make the word alignments worse, would the Ryan McDonald model do better because they have a subsequent training that doesn't entirely trust the word alignment, right? If I remember it correctly. But in your case...
You mean the McDonald's word product transfer parser? Yeah. I think... actually, I have not think about this, but you know, McDonald's work is a kind of weakly supervised learning. So if the word alignment was worse than now, I think yes, of course it will lower the accuracy of the lower the parsing accuracy, but I don't think that our approach will. I don't think this will be a bigger factor for our approach, since that.
Let's thank our speaker. Okay. So the second paper for this session is graph-based posterior regularization for semi-supervised structure prediction, and is presented by Luheng He.
Can you hear me?
Okay.
Yes, it's working.
Is the mic on?
It's on. Oh, okay.
Yeah,
great.
yeah, it's working.
Hi, I'm Luheng. I'm a student at UW. Today, I'm going to tell you about how to use graph propagation to help semi-supervised part-speech tagging, and especially how we did it by simply optimizing a joint objective function. This is joint work with Jennifer Gillenwater and Ben Taskar. And this work has originally been presented at Kano 2013. Here's an overview of my talk today. First, I'm going to talk about structured prediction, in particular conditional random field, with its application to part-speech tagging. And then I'll talk about graph propagation, which is an alternative approach to do part-speech tagging. It's like semi-supervised and instance-based method. And finally, I will talk about how we successfully combine these two very different methods into a single joint objective function that can be efficiently optimized. So I guess most of you are familiar with part-speech tagging. Basically, for each word in a sentence, we want to assign to it a syntactic category, such as a determiner, a noun, a verb. So for each instance, we have the input x, which is simply the sentence, and the output structure y is the sequence of part-speech tags. Conditional random field is a standard technique for doing part-speech tagging, and its tagging prediction is based on the feature function f that is defined on each of the local factors in the output structure y. It usually contains the current tag yt, the previous tag yt-1, and the input x. And also, we have a set of parameters theta, which are the feature weights. So use theta and the feature function f, we can compute the potential scores for each of the local factors. Therefore, we can model the conditional distribution for all possible tagging sequence given an input sequence x. In particular, p theta of y given x is the conditional probability of a particular tagging sequence y given an input x. It is computed by taking the product of all the local factor scores and normalized to sum up to 1. So, therefore, learning the conditional random field model can be formulated as an optimization problem where we want to choose the best parameters theta to minimize the negative log likelihood of all the labeled sentences from x1 through xl. And different from conditional random field, graph propagation is an instance-based method, and it tries to predict one tag at a time without considering any structure information. In our particular setting, each input is a trigram in the sentence, and the output is the part-speech tag of the center word in the trigram. The basic assumption is that if two words frequently co-occur in similar contexts, then they should be assigned with similar part-speech tags. So to apply this assumption, we start by building a sparse k-nearest neighbor graph using all the trigrams that occur in the corpus as nodes, and for each pair of trigram, we compare the distributional similarity using the words that's around in the context of the trigram and inside the trigram. And for trigrams that are similar enough, we add an edge between them with edge scores representing the similarity scores. So if a trigram ever occurred in a labeled sentence, we consider the corresponding node as labeled, otherwise it's unlabeled. Then we can propagate information from those labeled nodes to the unlabeled nodes. And this gives us a tagging distribution of the center word for each unlabeled trigram. And formally, this tagging distribution is determined by choosing the one that minimizes its difference with its neighbors. A final step is to sum over the entire graph and write a quadratic penalty term. We call it a graph Laplacian regularizer. This regularizer forces the tagging distribution for similar trigrams to agree with each other. So again, graph propagation can be formulated as another optimization problem where we want to choose the best tagging distribution to minimize this graph Laplacian regularizer term. Now take a step back. We talked about two very different methods to do part-speech tagging. The first one is conditional random fill, which is a supervised method that learns from labeled data, and it models the conditional distribution of all possible taggings given an input sequence, and it's parameterized by theta. And we also talked about graph propagation, which builds a k-nearest neighbor similarity graph from labeled and unlabeled data and propagates information across that similarity graph. It models the tagging distribution for the center word for each unlabeled trigram. In the next few slides, I'll talk about how we can combine these two methods. There's some prior work that tries to do this. The work that's most related to us is by Subramania et al. At NLP 2010. They use an iterating method that first train a conditional random field from the labeled data, then use the CRF prediction to initialize for the graph propagation, and then use the graph propagation's results to provide additional training data for the CRF. And this goes on for many iterations. So this work is empirically successful, but it also raises several questions, such as, is it optimizing some joint objective, or does it have a guarantee to converge? And these questions actually motivated our work to build a joint framework that has nice guarantees. A first step to do this is to introduce a set of auxiliary variables Q. You can consider it as a copy of the conditional distribution as p theta. So in particular, QIY models the conditional probability of a particular tagging sequence y given an input xi. And we make two further assumptions on the conditional distribution Q. One, that because Q is a probability distribution, it should be normalized to sum up to 1 for each sentence. And second, we assume that Q can be decomposed exactly the same way as P theta does. So we can write each QIY as a product of a bunch of local factor scores. We call them R. And later we'll see that these assumptions are crucial to our efficient optimization. Now with the auxiliary distribution Q, can write our joint objective function. It consists of 3 parts. The first part is the graph Laplacian regularizer that's defined on the distribution Q, and the tagging distribution for each trigram is computed by normalizing Q with respect to each trigram in each tag. And the second part is simply the objective function of the conditional random field defined over p theta. So if we optimize the first 2 terms separately, we'll get 2 very different distributions that capture different information that's helpful for part-speech tagging. So we have the final term that minimizes the k-out divergence between the 2 distributions, q and p theta. Basically, this term forces q and p theta to agree with each other so that the final prediction can benefit from both the graph propagation information and the conditional random field information. So the final question remains is that how we can optimize this joint objective efficiently. We have 2 sets of parameters, q and theta. Theta, remember, are the feature weights in the conditional random field. It's completely unconstrained, so it can take any positive or negative value. So optimizing for theta is very easy. We just do a straightforward gradient descent method. However, updating q is more complicated for 2 reasons. The first one is that q is constrained to sum up to 1. And second, there's no compact representation for Q. Remember that for each sentence xi, the number of all possible taggings y equals to the number of all tags raised to the power of sentence length. So basically, there are exponential number of components in the distribution Q, and it's simply impossible to memorize or update that many variables. However, we still want to do this. Remember, we made an assumption that Q can be decomposed as a product of local factors R. So it's natural to think that what if instead of updating those Q variables, we want to maintain and update those R variables, and there are much less of those variables. But consider if we do an additive gradient update upon that Q, then what happens is that the resulting Q prime will no longer be able to be written as a product of local factors. Therefore, we need to use an algorithm called exponentiate gradient descent. So instead of an additive gradient, we do an multiplicative gradient update, which means we take the gradient term and take its exponential and multiply it to the original Q and resulting in the updated Q. When written as this form, we can see that both the original Q and the gradient term can be decomposed into a set of local factors. We omitted the details here, but basically we can write the gradient term into a bunch of local factors and distribute those local factors onto each of the R variables. This means that instead of updating all the Q variables, we only need to maintain and update those R variables and then compute the Q using a forward-backward algorithm. So to summarize, we have two sets of conditional distributions, Q and P theta, and we have this joint objective function. We can optimize it using an EM-style algorithm, where at M step, we update theta, and at E step, we update each local factors in Q, which are the R variables, and we can normalize Q by doing a forward-backward. And this algorithm is guaranteed to converge the local optimum. Now we come to the experiments. We tested our algorithm on 10 different languages from the kernel data set. And we tested under a weakly supervised setting, which means for each language, we use only 100 labeled examples. We used universal part speech tagging set, so it's the same tag set for all the languages. And for the base model, we use a second-order conditional random field. Here's our results. On the x-axis are the 10 different languages, starting from English, and on the rightmost bar is the average of all the languages. And the bars show here part speech tagging errors, so the lower the better. The first baseline we're comparing against is the graph propagation results, which is simply by minimizing the first term in our objective function. And the second baseline is computed by learning a conditional random field from the graph propagation result for one single iteration. It has some improvements, but not much. And the third baseline is simply by training a conditional random field using the 100 label examples. So it actually outperforms the previous baselines for some languages. It tells us two things. One is that structural information is really important. The other is that graph propagation provides additional information as well as additional noise. So finally, we have our joint objective, which combines the power of the previous two methods. It outperforms previous baselines for all languages consistently. It has a 28% relative error reduction on average. So as a conclusion, we want to use graph propagation to help weakly supervised structured prediction. In particular, we formulated this graph propagation method into a regularizer term and encoded it in a joint objective function. And we also proposed an efficient algorithm for optimizing this joint objective. And it is more interesting to think about that what other kinds of posterior constraints that we can use to help structured prediction? We can use it as long as it can be written as any convex and differentiable regularizer term. Our code can be found at the link below. You can try it out and play with it. Thank you for your attention, and I'm happy to answer questions.
Any questions?
So, am I right in thinking that you are forcing the graph to do a prediction on every single eye in the chain?
It's not exactly. It's all the trigrams. So if two eye positions have the same trigrams, they are combined into the same node. And
right. But in your joint objective, could you use the CRF for known words? So I guess another way to ask the question is that the graph in the Subramania work could be sparser. Doesn't have to predict on everything, right? Because they take the average. They sort of do self-training in order to combine the prediction of the graph and the CRF. Whereas you have a full joint model.
Yeah, but the graph regularizer is still based on the tagging distribution for each node, and the node is marginalized and normalized, basically taking an average over all the label data. Am I understanding it right?
So I mean, you could use the Subramania method without forcing the graph to label every single word in your training data. Right? You could use it for, let's say, unknown words. But in this one, you have to do it on every single.
Yeah, the graph contains information about all the tokens.
Okay, I just wanted to it's just a question about the model. I just wanted to understand it better.
Thank you.
So I just wondering, usually how fast will the EM steps converge?
We ran it for 20 iterations.
Okay, is that different by languages?
For larger languages, slower, of course.
Okay, cool.
We have time for a quick question. Okay. Otherwise, let's thank our speaker again. All right. Okay, our next and final talk for today. We kept the best for the for the end is multi-metric optimization using Ensemble tuning, and Anoop Sarkar is presenting.
So you know that 2 out of the 3 co-chairs are my students because they put me as the last talk. This is their way of getting revenge on me. So I'm going to talk about this work that was done by primarily by my student Baskaran, who couldn't be here today. So I'm presenting on his behalf and also on behalf of Kevin, who's in Nara, in Japan. He's our collaborator in this work, and it's about multi-metric optimization. So I'm going to start with a caricature of how we do discriminative training in MT, and this has 2 objectives. If you already know how it works, then it will introduce you to the caricature I'm going to use to explain what we did. And if you don't know how MT tuning works, then this will give you a distorted view of what it does, and at least enough to hopefully understand our contribution. So we start with a French sentence there, and English sentence here, which is the translation of that French sentence. This is a machine translation decoder, which is going to produce what the machine translation system currently thinks is the translation of that French sentence. So you can get an n-best output for this French sentence. And we're trying to tune the parameters of the model. So what we want to do is to use these n-best lists in order to train the parameters of a model. So we have a bunch of knobs that we want to turn in order to make sure that the translations we get in that n-best list matches the actual translation of f, right? So we might get something wrong, and we want to tune these knobs so that in the next iteration we use a better weight vector, and that better weight vector goes back into a decoder, and hopefully we get better. So this is our tuning loop. We're training our system to produce better machine translation outputs. So the question is how to choose this weight? Well, this weight is something that's going to match an extrinsic score. So, a loss function of some kind. And that loss is based on some metric. So some way of saying that this is a good translation or this is a bad translation. And machine translation is notoriously difficult because there's more than one way to translate a sentence. So you don't get a loss that's quite nice like you usually do in machine translation. So let's look at this weight optimization step. We want to say if the model likes it and the metric likes it, that's great. Our model score is good and it also performs well according to the metric. If our model score is really high and our metric says this is bad, then we should be changing our weights. If, in this case, maybe they're both good. In some cases, the model score is bad and the metric says it's bad, and that's good too, right? So we're sort of predicting that this should be bad. So here's one particular metric. It's called blue. It just basically matches n-grams in the output with the reference. And they might be, and this is, and the x-axis is a model score. So you can see that this guy and this guy are kind of evil twins, right? So this has a high model score and really good on our metric, so higher the better. And this is really good model score, but terrible on our metric. So what we really want to do is say, here's two things that are getting high model score. Prefer this guy over this guy. So you can kind of replace this complicated machine translation loss function into something that is basically binary classification, right? So this is the idea behind PRO. So the question is, is this metric the most suitable one? So you go to, it's happening less often for some reason, but every time you go to an ACL or an ACL, somebody in the audience will get up and say, I hate the blue score. When is the blue score going to end? And lots of people have tried many, many replacements for the blue score. You can take your pick. There's a whole bunch of different metrics. So each of them can be used to choose a weight vector that matches one of these extrinsic scores. But when you look at every single paper on machine translation, you optimize using blue. And it's the Highlander of machine translation metrics. There can be only one. It has killed everything else. And it is true, it does work better. So people have tried other metrics. It just seems to be the best one. But in this work, we want to say maybe you don't have to choose one. Maybe we can be sort of anti-Highlander and have many people live. So in this work, we're actually going to look at different metrics and see how we can use them all in order to tell us what's a good translation, what's a bad translation, all at the same time. And so we have the blue score. It's n-gram matches. We have a meteor, Alon Levy's favorite one. It's like blue, but unlike, so blue is essentially captures recall in a funny way. So meteor captures precision and recall, and also has some synonym and stem matching. There's a one that you might not have heard of. It's called Ribus. And Ribus is really good at figuring out whether things are out of order or not. So it's very popular for Japanese English translation because it measures out of order matches. It does it using a Spearman's correlation coefficient. And finally, there's a good old one from the speech record days, which is word error rate. So this is translation error rate. So it insertion, deletion, and block shifts. Okay, so these are all different reasonable ways to measure how different is your hypothesis from the reference. So what we're going to do is use them all at the same time. So let's define what that means. We want to find the weight vector that's good according to multiple metrics. Okay, so this is kind of a hand-wavy way to say that. So find one W that simultaneously optimizes many different objectives. Each metric is treated as an objective, and you treat the hypotheses that we produce for each metric. And G is the way to combine them. So one way to do it is to simply, at this point, when you choose a weight vector, just take two things like ter minus blue divided by 2. Just combine them together, and now you have a linear combination of two different metrics. Okay? And this has been done before. This is going to be our baseline. There's one problem with this is if you want to combine them and you want to say, I want to actually have more weight on the blue score and less weight on the error rate, you have to do that by hand. There's no automatic way to do it. So we're going to address that issue, and we're going to do things a bit differently. So what is a reasonable way to combine different metrics? Well, one reasonable way to do that is a notion of Pareto efficiency, which says you have optimality with respect to different metrics. Then you should look at these objective A and objective B and look at this frontier, right? So these points here don't matter. They're worse according to both metrics. So these points on the frontier are the ones you should be looking at. So this is the idea we're going to use. There's previous work by Kevin that actually just modifies pro to push the points in the frontier. But one problem that was in that previous work was there was no way to actually take advice from all the different objectives at the same time. And that's another problem we solve in this work. Okay, so I'm not going to present three of we introduced 4 different ways of doing it. And I'm just going to present our main result due to lack of time. And I'm going to explain to you what it does using my caricature of tuning. And we call it ensemble tuning. And the idea is the same as before. You get your n-best output, nothing different here. Now, if you have, for example, blue as one of your objectives, you do blue weight optimization. So you turn the knob so that you get the best weight that is going to optimize blue. And let's say the other metric is meteor. You do that as well. You get another weight vector. So you get 2 different weight vectors, W1 and W2. And they both have different views on what the weight vector should be, right? And now what we do is we combine these using these meta weights. The meta weights are saying how much should I trust blue, how much should I trust meteor. And the meta weights are trained so that the points that we pick, that is a combination of these two, lie on the Pareto frontier. Okay, so it will reward things that are on the Pareto frontier, and everything under that frontier will get penalized. Okay. Now, there's one issue here, which is when I combine these two, I still want one model. I don't want a blue model and a meteor model, because now I have two problems, not one, right? Before I had at least one problem. So I need a way to combine the predictions of the blue model with the error rate model, or meteor model in this case. Okay, so how do we deal with these multiple components? So that's the second problem we solve, is you don't have to pick and choose. So usually when you do Pareto optimality, the usual way people use Pareto optimality is they say, well, somebody else is going to pick one of these, depending on what you want. So if you really want blue scores, you would pick this one. If you really want meteor scores, maybe you would pick this one. So we don't actually have to make that choice. We combine the weights using ensemble decoding. And the idea behind ensemble decoding is very simple. We have weight 1 and weight 2, right? One is a blue, one is a meteor. And whenever we make a prediction, we actually combine them together to make a prediction while we're decoding. So basically, we can take as many weight vectors as we want and produce something that will be the combination of these. And we just do that all the way up until we get a translation. And each case is going to be a combination of these two weight vectors. Okay. So we implemented this ensemble decoding idea as well as the Pareto weight training in our favorite decoder, which we wrote, which is available on GitHub if you want to use it, if you're brave enough. We use fairly standard large-scale corpora, Arabic, English, and Chinese English. And this is going to be two-dimensional. So this one is ribus and blue. And I'll show you results for other metrics. But let's just look at blue on one axis and ribus, which is another empty metric on the other axis. And LC, so blue by itself is over there. Ribus by itself is over there. So you can see that if you optimize towards blue, you do better on blue. If you optimize on ribus, you do better on ribus. That's LC points are the linear combination points. This is linear combination plus ensemble. And that point up on the right is blue, ribus, and ter all together. And this point over here, I guess I point here. This point over here is blue and ribus together. So you can see that what we want is points that are on the upper right quadrant, right? Things that are good according to both metrics. And ideally better than both, either doing one or the other individually. Here's Chinese English. And you can see that as you add more metrics, you can get a bit better. It's better on blue than just doing blue itself. It's not, so in this case, it's not as good as doing meteor by itself. But you can see that meteor scores really badly on blue, right? So the question is, are those points up there good because you get a good blue score? So can you always improve the blue score? So here, actually, we show that if you have a single objective, this just blue gets better. If you have two metrics, blue and ribus does better. This is blue meteor ribus, blue meteor ter are both better than just doing blue. And then we did some crazy stuff over here with like B3 is like blue 3 gram instead of 4 gram and so on. So you can invent as many metrics as you want. And so you can see that in fact does better. So we also tried to look at whether those points on the upper right quadrant are actually better. Do they actually read better? So we did a human evaluation, which was a post-editing task, and we saw a 6% gain in the post-editing error rate. So it was 6% easier to post-edit multiple metrics than one metric. And that's it.
Okay, do you have any question?
I just wonder if you find any language difference in preferring one matrix over the other.
So Kevin has done work on Japanese English, and Ribus helps more for Japanese English just because of the reordering. And we haven't done anything other than Arabic English and Chinese English yet.
Yeah, since you use a combination of multiple metrics.
It's conceivable that you could have some metrics that help more with languages that are quite different. I don't know, if you had a really good metric for morphologically complex languages, which doesn't exist, but if you had one, then we could use that in order to improve the BLUE score.
So if in that case, and then when you combine multiple metrics, and then you have to take that into consideration.
Yeah. But I mean, it's an interesting challenge, at least. It's not just mindless, right? So, in some sense. I think that's an interesting problem to have.
I didn't 100% understand why you needed to combine the weights on the fly during inference as opposed to combining them offline into a single model.
Oh yeah, it does better. That's what we claim. We have a lot of...
Works for me.
I agree, it's not a given, but we have compared it to linear combination offline, and ensemble decoding allows you to do different things. So it allows you to, for example, do switching, which you can't do.
I see. So you're not just, okay.
Yeah, it allows you to do different kinds of voting. So we have different ways of combining the models that you can sort of turn off and on in the decoder.
Oh, okay. So you're learning combination methods.
Yeah, so Majid's thesis is on that. So
makes sense.
We have a lot of papers on ensemble decoding as our hammer that improves over linear combination.
So I'm surprised that when you optimize both BLUE and Meteor, for example, that you can do better on BLUE than just optimizing on BLUE alone. Right?
But it's not surprising.
It's not surprising?
Well, you can think of BLUE as being very, very sensitive to length, but actually maybe it shouldn't be, right? Like in some cases it might penalize it really badly because you hit against a brevity penalty, and that leads you into a bad space.
So I can see why optimizing both metrics at the same time would do better for humans, but just on the BLUE metric alone.
Yeah, it just stops BLUE from making a mistake that's a story you could tell. I don't know. We have tried to analyze it in different ways. So Baskaran has done some things where he sort of, on purpose, sort of damages one metric and then sees what you can recover from the other metric. It's kind of interesting to see, but those are still artificial. We can't. You can't tell. There's an interesting paper by the BBN guys, I think, about putting together a bunch of different features to sort of get BLUE on the right track, so as it were. And this might be what's happening here as well.
Thanks.
Yeah.
Okay, so let's thank our speaker again. And I think now we have some closing remarks.
Hi, I'm Ann Clifton. I'm a PhD student at Simon Fraser with Anoop, and one of your co-chairs today. So just really quickly, I wanted to thank all of you for participating today and making this the most successful Northwest NLP to date. And in particular, I would like to take a moment to thank our hosts here at Microsoft, particularly Will Lewis, who's set all this up for us. So I hope you join me. So that's all. Thanks for coming. Hope to see you in 2016.
Before you leave, I do want to mention that actually I'm getting almost too much credit here. Anne, Anoop, Mariam, and Yashar, Yashar, did an enormous amount of work, and this honestly is the most successful by number NWNLP that we've had. if we continue at this rate, we're going to have to move to a much bigger venue next time. So hopefully we don't double yet again next time. Let's try to keep it around 300 next time maybe, and then we'll be okay. Okay. Thank you, everyone.